Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everyone. Today is the last day of Joshua Schiffman's internship. He comes to us from Penn State University, where after this internship, he will resume being advised by Trent Jager. When he joined us, he was already an expert in trusted computing, so we were able to put him to work right away on doing personalized services in a privacy-preserving manner.
Thank you. Hello? Anyway. All right, good. You guys can hear me. All right, thank you for the introduction. So before I start, I just want to thank Jay and Brian for the excellent internship. It was my pleasure. And let's see. Okay, so I'll get started. As Jay mentioned, this work is that I did over the summer is on building personalized services that also protect the user's privacy. So I'll just get started. All right. So why personalized services? Well, these services add value and relevance by using personal information of the users to enhance whatever it is they're delivering. So a good example is targeted advertisements. I'm sure every person out here would prefer not to receive advertisements that are targeted towards an age or demographic group that is not related to them in any way. Like, for instance, I don't want to receive any ads for feminine hygiene products. And I'm sure the marketing department of these companies also don't want to waste money delivering these ads to people who don't care about it. And then location-based services, search, all of these things benefit from user information like search history in order to perform optimization on search results. Unfortunately, the value of these services is directly related to how much information the user is willing to give up. And in the case of, say, location-based services, you're giving away your GPS coordinates, for example, or with social media plugins, I can look at what my friends are reading, but they can also look at what I'm reading. So it's a two-way street. So as everyone's well aware of, all the recent lawsuits against large corporations like Apple and other companies that have been caught collecting personal information about users, there's a desire to enable the client or the user to be able to manage or protect their own private information. And current regulation and upcoming regulation like Do Not Track express this in legal form. Unfortunately, it's difficult to manage this information and still use these services to their full extent because you need to explicitly release your personally identifiable information if you want to get the benefit of the service in many situations. And yes?
It's not a regulatory framework, Do Not Track. It's just a simple recommendation.
Okay. Thank you. Yeah, I have been looking at proposals of some lawmakers that want to try and put this into more of a strict framework, but yes, you're absolutely correct. The current existing framework is just a suggestion at this point. So yes, even with the stronger regulation in place, there's no guarantee to the regular client that their information is actually being maintained properly. So if Microsoft says that we will keep your information private, and then later a compromise occurs at Microsoft, not necessarily their fault, information has been lost, and the user is out of luck. So our goal is to provide services to the client in a way that's going to allow them to protect their privacy, but also still maintain the utility of the service. So far, several approaches have been worked on, and mostly they focus on client-side solutions. And this is attractive because you don't need to modify the application that the service that you're using. You can opt into it, and moreover, you can verify that it's working correctly because it's working on your device. Your device controls the release of your information, so it's very useful to be able to have the control there. And there are several categories of these approaches. One is to control how the data is released. So for example, you can release the information in an obfuscated manner. You can say, instead of my GPS coordinate to a location-based service, you can give a general region or a fuzzed location, or give out the information less often. So in, like, for example, Google Latitude or Foursquare, you may update your information less often as opposed to every 5 seconds. The problem with messing with your personal information, obfuscating it, is that it reduces the utility of the service. So if you want to, say, find a coffee shop near Building 99, and you say, I'm in Washington, that's a little bit harder to service that request. And also you have to do additional processing on your, say, mobile device or whatever you're using to get the actual result you wanted. Another option is to perform the personalization locally, and this sort of mixes with what the first category was. So services like Search on the Go will collect, at the beginning of the day, various links that are popular or that related users have looked at in the past, so that you don't have to query a server often. And this has an added bonus of being privacy preserving, because it's not quite clear what it is the user is looking at if all the personalization is being done on the device. And likewise, Retrieve and Privad will try to hide the user's interests by doing personalization locally, like search optimization, and also, say, subscribing, in the case of Privad, to a large category of advertisements and only selecting locally the ones that are interesting to that user. And in the case of this category, one of the drawbacks is that you also have to have a very large database locally of all the information that is relevant to what you're looking for. And also this might be prohibitive, bandwidth prohibitive for mobile devices if you have to use, say, services that are updating constantly. So you can't really cache new information ahead of time if you don't know it's being updated. And finally, there are other approaches that try to remove linkability, say with mixed networks, Tor, or proxies. This will hide your, say, IP address, but there's still aspects of what you're using the service for that may reveal who you are. So for example, if you're using a web proxy, social plugins may give away your user ID, for example. So even though your IP address is hidden, you're still in trouble. So to summarize, some of the drawbacks of the client-side approaches are that you have an increased burden on the client, obviously, potentially higher bandwidth and storage requirements, more processing locally, and also messing with the information you're giving to these services will reduce their utility. So can we do better than this and still ensure information privacy? Our approach is to look at a server-side approach. Yes?
How big is the burden on the client in terms of storage? Because it seems like storage and bandwidth could potentially be traded off a little bit.
Yes.
You have to get the storage on, but instantaneous bandwidth usage.
Right. So this is going to be absolutely domain-specific, depending on the service that you're trying to provide. We're looking at a general approach, but you're right. For services that, say, there's constantly updating information, you could potentially cache a very large set. For example, map tiles. If you could cache all of Washington, then yeah, you could take care of that. So like I said, our approach is to look at the server-side solution instead of a client-side solution. And the reasons for doing this is that we get to leverage a few nice features of being at the server that's offering the service. One is we have a massive amount of resources. We have high bandwidth connections to the services that are offering or that are being offered to the client. We also have access to potentially aggregate information. So in the case of a client-side solution, you're siloing everyone's information. And if you have some sort of trusted third party running in the server, then you could potentially aggregate this information in a safe way. So as I mentioned, there's sort of two requirements that you want to achieve if you're going to be providing a server-side solution, because no longer your solution is at the client's device and they're not able to check it anymore. And that leads into these two requirements. One is protection. You need to be able to ensure that the solution is safe from tampering by malicious parties. And this includes not just external network attackers, but also physical attackers. So malicious admins working in the company, or also people who may, say, want to put probes onto the device and read out whatever keys or secrets are stored there. And you also want to be able to verify as a client that this remote party is working correctly on your behalf. You want to be able to verify that the device you're giving your secret information to is the correct device, and then it's running the code that will protect your private information. So what kind of protected modules can we create? There's two major categories that I'm dividing them into. One I'm calling software-based, in the sense that the software is protecting itself. Yes?
What is the you assume that the client is completely secure? Because the client could potentially just take the information and send it to some other server instead of your trusted server, and then what's the point?
Right. So our threat model here is that the service that's offering whatever to the client is potentially untrusted, so they may be curious about what it is you're looking for, and they will gather any of your personal information, maybe sell it to third parties. Even if they're not interested in doing that, there may be a rogue element within the company that wants to, say, look at the personal information that's being collected. So we're trying to come up with a solution that will maintain the user's privacy from, say, these sort of attacks.
But the client itself is secure. So whatever application you run on the client, that's not going to ship off the client street or something.
That's right. We're assuming the client is trusted. Right, so the two major categories of protected modules I'm looking at are what I'm calling software-based and hardware-based. And when I say software-based, I mean that the protections are based in software, but verification is still based in hardware. So in particular, we're looking at a TPM-based verification system. And there's two major related work here. One is Flickr, that is a system for executing a small binary in a trusted environment that is protected from, say, the underlying operating system and any potential rootkits that are resident there. And the Flickr system lets a remote client verify that this protected module is running the correct code that they want to use and that it's on the correct machine that they're expecting. TrustVisor took this a little bit further and virtualized the features of the TPM in order to improve performance. And HyperSafe is a research project here at Microsoft that Himanshu is working on based on Hyper-V, which focuses on protecting a virtual machine running on the hypervisor and separating it from a potentially untrusted root partition, the management VM that's in charge of devices, for example, to that VM. On the hardware-based front, there are several security coprocessors, such as the IBM crypto coprocessors, which cost on the order of $10,000 or so. And these devices are fairly beefy. They have all kinds of sensors on them that can detect changes in temperature, voltage, light, people sticking probes onto them, and they'll self-destruct if you start cracking them open or leave them on a pallet outside of Nome, Alaska. And they also have fairly powerful buses and CPUs inside by crypto card standards, not by general PC standards. But they're pretty powerful. On the exact opposite end are the Infineon SLE chips. These are essentially the smart cards here you can see in the middle. And these devices have about a 50 megahertz coprocessor, about a USB 1.0 bus, and are very low power. And they also have various sensors and protections to make sure you're not tampering with the devices. And then finally, I mentioned FPGAs here because, well, you can do a lot of things with these devices, including sticking security protections onto them, tamper-evident sensors. So I looked over the summer on two different fronts, one with the software-based solution, one with the hardware-based solution. We came up with two different projects. In the first project, we looked at how we can design a general-purpose platform for privacy-preserving personal services. And to that end, we used HyperSafe to implement these trusted modules as protected VMs. And I'll go into that, how that works. And we designed an example application that does location-based search with Bing Maps, or Bing Local, actually. And the protected module will deobfuscate user queries for them so that they don't have to handle large amounts of results coming back from Bing, and protecting the user's actual location from the untrusted service. And then the second application we looked at is applying the hardware security modules to hiding access patterns in public data sets. So for example, Bing Maps again. Even if you have encrypted data sets or large public data sets, you still may want to hide exactly what it is you're looking at. So if you're looking for driving directions, for example, from your office to another location, even if you use Tor, say, to hide who you are, Bing may see that you're driving from Building 99 to some place, so they could figure out that you're a Microsoft employee. And even if you encrypted all the map tiles, well, they can still get an idea of access patterns to infer what those tiles were. So we looked at a scheme that employs these security modules to implement various PIR schemes in an efficient manner. So for our first project, we looked at location-based search. And simply, location-based search takes your GPS coordinates and whatever you're looking for and gives you back a ordered list that's from distance order from wherever you are. And if you wanted to hide your exact location but still use the service, a straw man solution would be to, say, obfuscate your location. Say I'm in like I said, Washington State instead of Building 99. And then you'll have to parse lots of results coming back. So our solution is to leverage the protected module to do the deobfuscation for the client, so they don't have to do all that, but still have a simple interface. So just as a simple illustration, the way that this our solution works is that the client here is going to provide a obfuscated query, coffee in the Washington State area, to Bing Maps. And along with that is going to be the actual location of the user encrypted, along with the location, which is also signed by the user's public key or private key. And this is encrypted under the public key of our trusted module down here. So the client's public key is also included so that the public module can, or the private module can return the results. So this whole blob is passed to Bing. Bing returns the actual result that was requested, which was basically 7 million coffee shops in the Washington State area. Along with these results, they're passed to the protected module and the other parameters. The module will decrypt the actual coordinates of the user and then filter out the results to what they exactly wanted, re-encrypt it under the client's public key, and pass it back to the client. Yes?
Does Bing actually return all the coffee shops in Washington if you ask this query?
If you send enough repeated queries incrementing the search ordinal, yeah.
Because I was thinking one bad thing this can do is this is, well, one, if Bing actually returned a million queries, that would be a very bad design. But I'm glad to hear that it makes you do multiple queries.
Yes.
But if you do multiple queries, you are wasting client resources. I'm thinking of having a mobile phone, right?
Mm-hmm.
And
Why would you be wasting client resources?
bandwidth?
Well, so this is being done at Bing and sent to the protected module locally inside of Bing servers.
So
Bing
I'm able
data
to
center.
one query? I'm confused.
Right, so this protected module is actually going to reside in the data center, Bing's data center.
So
the query is going to be sent to Bing, and
Oh, the protected module would make multiple. Okay,
Yes.
okay, sorry.
yeah, it's a little, yes,
Okay.
it's not 100% clear.
But then does it still increase the load on the Bing backend servers?
Yes, that
by
would.
several large orders of magnitude?
Yes.
A
Yes, it would.
million is perhaps.
So you probably don't need to obfuscate that much. You probably could say something like 3-city area instead of that. And you under our implementation, you can limit the query to be something less than 1 million results. I think you've sufficiently hid yourself in that situation. Yes.
So if that information is encrypted, doesn't that require the client to have a key corresponding to one particular TPM?
Right. So in this situation, yes, you would have a single module that's in charge of that.
So you're going to elaborate on how you...
Right. So our current implementation, we're using a single system. We haven't looked at how to do it under load balancing, but that would be the next step. Yes.
So what's the privacy risk here that you're trying to protect?
We're trying to keep the user's actual location hidden from Bing.
Right, but if as long as the query doesn't have user ID or cookie, how would Bing know that it's from you? It's my location, or someone, or as opposed to someone else's location?
Well, it will still have your IP address when you make the request.
Right. So, but presumably, if this trusted module is sitting in some data center and it just sends to Bing just exact location, but with
That's good.
like someone else's cookie
Right.
or its own cookie, then
Well, Bing can still see when results or when requests are coming into their data center. So this box is not sitting on the periphery of the data center; it's within it. So presumably, they can observe network traffic coming in.
It has to sit on the periphery, right? Because you said that it's going to take the query and it's going to split it into potentially multiple queries going to Bing.
Right. I mean, it's on the periphery of Bing Maps service, but it's still within Microsoft's like IP.
But
range,
then
so
the
it's-
question is still there because it can act as a proxy and it can just say, hey, that IP address is 10.0.1.1 or whatever, right? And you would never know. All it has to do is to maintain a mapping between the standard NAT, right? This TPM model, all it has to do is like a standard NAT. And
So
your
you're saying
privacy
something
layer.
like
Then you don't need
well-
a TPM, you can just have a proxy.
That
that's what I was-
trusted proxy,
is
whatever.
one solution and it requires none of that.
Right, I'm just trying to abstract what Kane said. All you have to do is to cloak the ID and then that's it. You're not violating anybody's privacy, right?
Well, so in particular, we're saving the client from having to receive all the results back from Bing if they're providing a obfuscated query. So in addition to trying to protect the user's personal information, we're also trying to save the user bandwidth and effort having to parse through all those requests.
No. So what you would do is you would just make a real building 99. Okay? The TPM module or whatever this proxy is would of course get simply your IP address. So Bing will return only one result, and then the trusted module will, send it back with the right IP address. That's all. And in fact, all the web queries going out of Microsoft look exactly kind of like this, right?
Right.
If you exclude the cookie part, the internal IP addresses are not visible.
Then if Bing wants to know, it can still do traffic analysis. It still sees the request go into the TPM and the request come out of the TPM. So there exists a set of proxy solutions where you can secure your proxy. And for those, you don't even really need a TPM. So it seems like those are a completely separate issue. This is for if you don't want to rely on a proxy, if you want your request to go straight to Bing. It's a different set of solutions.
I mean, there are attacks on various proxies. So I mean, you could have, if you do trust the proxy to completely obfuscate or hide where you are, and be resistant to traffic analysis and all of these other attacks on proxies, then that could be a viable solution for a particular type of personalized service. But you are revealing that you're at building 99, but for more specific cases where you're out in, say, the middle of the woods and a request comes for driving directions for this one house in the middle of nowhere, then even if you hide the IP address completely, you still know who's making that request.
Have you presented your threat model already?
Mm-hmm.
You have?
Right, so our threat model here is that the data center and any, for example, administrators would be collecting the personal information that's being provided to the service in order to customize the results, and may collect the information, and the user's concerned with the privacy of that information.
Where are the attackers? What kind of attackers?
So we're considering both network external attackers to the data center and also administrators within the data center.
So can the administrator observe the results and do traffic analysis?
To the, I'm sorry, between,
At the data center.
Yes.
So the data center
Yeah.
administrator could be attacked.
yes, that's true.
But the results are encrypted.
Sorry.
The results are encrypted though. So the exact query that was requested would be hidden.
People have down traffic analysis over encrypted data as well.
Mhm.
That's for things like SSH, where the amount of encrypted data, for example, varies based on.
You don't have those
Well,
problems.
no, they do have this problem. But it's orthogonal, right? I mean, if the size of the result for the coffee shop that's in one location is different than the size of the result for a coffee shop in a different location, then they will reveal. But there are known ways of hiding
Yeah,
that.
we currently
Yes.
pad it to a fixed
Yeah, that's the
size
answer.
in the response. Yeah, we currently pad our responses to a fixed size to deal with that
Yeah.
particularly.
Gotcha.
Okay. Right, so how we implemented this system, we used HyperSafe to create our protected module. What HyperSafe does is it provides a feature called emancipation. Normally, VMs running in Hyper-V have a root partition, which is responsible for virtualizing devices, for example, setting up the VM. And it always has access, normally under Hyper-V, to certain pages of memory of the VM. So if we want to verify our protected module, we also have to verify a large, potentially buggy TCB that includes the root VM, the root partition. So what emancipation lets us do is the VM is, the memory pages that are shared between the VM and the root partition are separated, they're unmapped, and the VMs, our trusted module, or the VM that we're loading, a hash of it is taken before it is executed. And so in a sense, this is like a virtual DRTM, if you're familiar with that, or virtual boot environment, essentially, a measured boot environment. So what a remote verifier has to do is just verify that the hypervisor code is trustworthy and that the VM itself is trustworthy, and no longer it has to verify the root partition. So on top of this system, we are then implementing our protected module as as a very small, minimal execution environment. And this is our TMK we're using to implement that. So what the TMK is essentially a program that stresses the various features of the hypervisor. And what we did is we took this TMK, which is roughly around 100 kilobytes, which has no OS or very crude memory manager support built into it. and we implemented our trusted service inside of this, which is going to do the personalization for the client. And the trusted module receives inputs from the untrusted service through a shim, which runs in the untrusted root partition. And this is presented on a single specially assigned shared memory region for the VM. So in order to verify this whole system, we have this following process. HyperSafe, when it's first booted, it uses the measured launch environment, which will record the code that's used to boot the entire process. So this includes the firmware. Well, actually, no. This includes the bootloader and the hypervisor itself. And this code is stored inside the TPM. And the TPM also will generate an RSA key pair for the HyperSafe hypervisor. And this key pair is then, well, the secret key is sealed under the actual measurements of the binaries that were loaded at boot time. And it's also signed by the TPM signing key. So only the particular HyperSafe binaries that were used to boot into the system can actually decrypt this key later at a later date. So we have a particular version of HyperSafe. It boots. We generate a key. The TPM seals it under that particular version of HyperSafe. And later, if it boots into a modified version of HyperSafe or a malicious one, it won't be able to access this key because it's protected by the physical TPM. Then once the HyperSafe hypervisor is loaded, it will measure and load the TMK. And it will also generate an RSA key pair for this protected module, and will sign the public key with the TMK's actual code hash. And then it will provide the secret key to the trusted module and put both of these public keys available on a public website so that a client can obtain them and know which key to encrypt the query under when it sends it to the trusted module. And it can also inspect the actual code that was used to boot into that system so it can see if it's trustworthy or not. Does anyone have any questions before I go past this? It's a little convoluted. Okay. So I'd like to give you a brief demo of the application we created. Okay, so let's see what I have here. I have two different machines. This machine is running the Windows Phone emulator, and this code is the client code for interacting with the protected module. The protected module is our TMK I mentioned before, running on a separate machine that is running HyperSafe, and there is a shim program running on that machine that is that the web service that's implementing our untrusted service communicates to. So what will happen is the client will send a request to the web service. The web service will essentially make queries to Bing to get back the results, pass these results to our TMK. It will do the personalization, gets back the response, and then sends it to our client. So I probably don't want to go through 3 levels of indirection to remote desktop into my other remote desktop through this remote desktop. So I'll just show you the client. All right. Okay, so this is our trusted search application, and we can provide a query that we want to search for. So I'm hungry, I look for pizza. And then we'll get our location. And then obfuscation level here, what this does is it essentially perturbs your current location to Bing, gives it random offsets, and then will also increase the radius search size. We can increase that to, let's go to 5. And then this number of results we can look for. So what will happen here is it takes a little bit to load. Right. Okay, so these are the nearest 10 pizza joints around here. Yeah, it's a little slow over remote desktop. But yeah, these are the various locations. And you can see they're ordered by distance from the user. So, I mean, looking up phone book directory information is exciting in its own right, but you get the basic idea of how this works. So on the back end, actually 100 queries have been retrieved, and they are from essentially over near the OTC pickup spot instead of here. So they're a little perturbed, but it's been relocated by our trusted module to this actual location. So there's not too much exciting going on here, unfortunately, but yeah, that's the demo. Any questions? Okay. Okay. So, yes.
11:05.
I'm sorry, you had a question?
So the phone presumably verifies the results that it gets back from the secured module.
Right.
Is this the usual? So I mean, you said the HyperSafe generates these keys, and then these all chain back to the TPM.
That's correct.
Okay.
That's correct, yeah. So it'll be signed under the TPM signing key, and then that key can be verified through either the platform key, or you can use other methods like direct anonymous attestation to verify that key. And then these keys, Microsoft, for example, could have a PKI internally for all of its devices, which I believe it does have. Okay. As an intern, I can't get access to the key fobs to remotely access the machines. So, going on to our second project, we looked, instead of using our software-based approaches with HyperSafe, we looked at using our hardware security modules. So, to give you some motivation here, we're looking at hiding access patterns to, say, a large set of public data, for example, Bing Maps. And oftentimes, the exact what you're looking for reveals information about who you are. Like I mentioned before, if you're making requests for driving directions, you're giving away information about where you're potentially located. So encryption is a natural way of hiding this information from untrusted servers, such as a cloud storage device. But even if the data is encrypted, the pattern in which you access the information may reveal exactly what is encrypted on the system, especially if some additional knowledge is given about what the data may be. So there are various schemes for retrieving this encrypted information to hide your access patterns, and these schemes are typically called private information retrieval. And as a simple example, consider the Bing Maps example I gave before. So this tile here is level 17 of the Bing Map tile database. Level 17 is roughly a 100 by 100 meter tile, give or take a few hundred meters. So a trivial PIR solution for hiding what exactly you're looking for is to access every element in the database. That's obviously infeasible for Bing Maps because there's 60 billion tiles, roughly. To get an idea of what our data set looked like, we did some experiments to evaluate how many tiles are there. And this is just the last few levels of the database. And as you can see, 17 and 19 are roughly where everyone looks at when you actually look at driving directions. This is, more or less. So after 19, the information available from satellites is so small that there's not really anything there, and everyone pretty much doesn't look at the continental-sized map tiles. So this is where most of our information is concerned. So our analysis looks at this data set here, in particular level 17. So how can we do something better than the trivial solution? One option is using oblivious RAM. So what oblivious RAM does is it gives you a sublinear amortized cost for doing private information retrieval on a database. I'm not going to go over the entire construction for oblivious RAM. There are various different schemes, but to give you an intuition of what's going on, and if you saw Mariana's talk, you probably already, earlier in the summer, you probably know about this. But the basic idea is that the information is encrypted under different keys for each epoch. And The information is retrieved in such a way that each record is only requested once, so that the untrusted server sees only random accesses to a single records within the database. And once all the records have either been touched or your cache that you're working on has been filled, you'll reshuffle everything under a new encryption key. You'll repermute everything. And so there are numerous schemes for doing this with different efficiencies. Some are better than others. Oftentimes, the worst case time for retrieving a single record can get really bad, especially if you've hit your budget and you need to reshuffle everything. So we need to look at a solution that makes sure that the worst case scenario is very good, so that we can actually have an online service. So we're considering here a new model. Under traditional models for ORAM, you typically have a single client interacting with a single server, or maybe two servers. And all the clients that are interacting with this untrusted server are typically non-cooperative parties. So they're not working together to improve the performance of ORAM in any way. And this doesn't allow for parallel retrieval or parallelism to improve the performance of ORAM in any way. So we're now considering a model where we have lots of clients all working together to serve a single goal, because our trusted modules essentially can serve a single client with high parallelism. So we'd like to be able to come up with a scheme or modify existing schemes that will leverage the hundreds of or thousands of coprocessors that are in the data center to improve the performance of our PIR scheme. And we'd also like to reduce the overall worst case access time and hopefully shuffling if possible. So just to, for anyone who's not familiar with ORAM, just to give you a brief idea of how one of the schemes would work. This is one of the simpler algorithms, often called the square root algorithm that Goldreich and Ostrowski presented. So the basic idea here is the ORAM data structure has two levels. The top level is typically called a cache, and this second level is your entire data set. So a client wanting to retrieve a particular record, and remember this, all these elements have been encrypted and permuted under usually a pseudo-random permutation. So if a client wants to retrieve a particular record, first he has to check that his cache doesn't have the record. So he'll scan through the top level. If it is found, he'll make a note of that. So if it was not there, he will actually go and retrieve the record and add it to the cache. If it was in the cache, then he will retrieve a dummy record, which has been added to the data set, or in some schemes, he'll retrieve just an unread record. So as you can see, over time, you'll have your cache fill up with requests, and you're only ever retrieving a record once. If it's been requested a second time, you'll retrieve some different record that hasn't been requested, or a dummy record. So once the cache has been filled, then you'll need to repermute everything in your data set, and that's where a large cost comes in, because there's, in Bing Maps, say, 60 billion tiles you have to reshuffle. So our goal, like I said earlier, is to support multiple users that want to interact with this database, and we want to minimize the worst case access time. So our basic idea is that we want to minimize, or we want to maximize the number of requests we can perform before a shuffle is necessary, so increase our cache size. Unfortunately, if you increase the cache size forever, then you have to linearly scan the entire cache size, and that would take too long. So we want to increase this cache size effectively without actually increasing the access time. And we want to perform, if possible, our request and shuffle in parallel. So say have a replicated data set that would be shuffling in the background while we're doing our request, and then we can swap over. This would be the ideal scenario, so you don't have to wait for a shuffle to occur. So our approach is to use thousands of these inexpensive SLE Infineon coprocessors, the ones I mentioned earlier that they're about $2 a piece, to do all this PIR scheme. And the coprocessors, because they're all working on a single data set unencrypted under the same key, we can serve multiple clients without the clients having to manage their own keys for encrypting the data. They'll just have to negotiate with the coprocessors. So our initial scheme for parallelizing the square root algorithm I showed you earlier, if you consider having C coprocessors here, probably 100,000 if possible, each with a cache size of k, and a single master coprocessor, which we will select in round-robin order to make sure that the caches stay balanced. All the coprocessors will scan their caches in parallel whenever a request comes in. And for each of the coprocessors that are not the master, this will be the first 2 lines here, we have the return value is going to be essentially the difference of 2 different PRFs. And what they're working on is creating essentially all the shares of a single record location that the untrusted server will then eventually retrieve. And we want to hide exactly which record is being requested so the server can't tell if it's a dummy or a actual record, because we don't want to reveal that a previously requested record was available. So the first line is going to be the difference of the 2 PRFs for the current coprocessor and the next coprocessor in the circular ring. And then the second line is if the coprocessor does detect that one of the records is in its cache, it will perturb the result a bit so that it will, the untrusted server will retrieve a dummy value instead of the correct value. And finally, the master record provides the actual address of the requested record. So if none of the other coprocessors have detected the requested record, it will simply request from the untrusted server the correct value. And if it was found, it will perturb it so that it requests a dummy value instead. So in this case, we have all of our coprocessors working in parallel. They don't need to communicate with each other. They use the untrusted server to do the retrieval for it. So then this response is sent back to the master coprocessor. In addition, all the slave coprocessors are going to write back an additional file to the untrusted server. And so we'll use this as an opportunity to pass the requested record to the master coprocessor so it doesn't have to receive it from all of the slave coprocessors simultaneously. So under this scheme here, if the record is present in the cache of one of the coprocessors, they will XOR this with a PRF of its coprocessor ID along with the next coprocessor ID. And if it has not been found, it will simply be a bunch of zeros XORed with those values. So these are all combined, XORed together on the untrusted server. If the record was not present in any of the coprocessors, it will essentially be a bunch of zeros that can be extracted by the master coprocessor when it XORs its own PRF value. If it was present, then it will get that value back and it can return that to the client. Any questions on this?
So if it returns a big file, does the client makes the request again, or what is the recovery?
I'm sorry, can you say again?
So if you're returning a fake file,
Mm-hmm.
right, what happens then? Because the client didn't get what it needed.
So the client will get the requested tile. What this scheme is doing is it's hiding from the server whether or not the requested tile was accessed previously. So if the tile wasn't in any of the caches, it will be retrieved from the server and the master node will send that back to the client. And if it was in the server, if it wasn't one of the caches, it will be combined into the second record that's sent to the master node, and it can be extracted from the combined XOR blob by just simply XORing its own PRF value here into that. So the actual record, if it was present in the caches, will be received by the master node, and if it wasn't in the caches, it will be retrieved by the server from the first round. Okay. So under the configuration of the SLE 78s, we were doing some investigation into that. We found that we could get, assuming an ideal bus speed of the USB 1.0 bus, we can get about a 70 millisecond response time from the entire level 17 Bing Maps database. Now this is an ideal bus speed. The devices probably won't be able to sustain the complete USB 1.0 bus speed, but we're looking into how we can get a better performance on that. Now the issue comes when you have to actually shuffle the entire data set, and we're exploring various ways of doing this. Under the current schemes that people have looked at, they typically use some sort of sorting network, such as a bitonic sorting network or other batcher sorting networks to implement the sorting. And the advantage of these sorting networks is that they maintain the oblivious property because the sorting is predetermined ahead of time. So you don't have to, basically, none of the sorting is done by examining the values of the records. It's just other than a simple comparison of two records. So we're looking at a Waxman permutation network that, we're looking at Waxman permutation network in order to improve the efficiency of the sorting. Currently, I can show you, so sorry, the axes are missing a few values at the bottom here. But the basic idea is that if you have, say, 100,000 coprocessors on the far right, again, with the ideal USB 1.0 bus, we can do sorting on level 17 in about 50 hours or so. That's probably way too long to actually do the scheme, but we are looking at ways of improving this. One option is to use a hybrid coprocessor approach. So as I mentioned before, those IBM crypto cards, which have a much faster bus, they have a PCI Express bus, which is on the order of gigabits transfer rate. So if we can employ those to do the sorting and use the SLEs to do the requests, then we might be able to match the performance. I don't have the chart included here, but if we had, say, just a USB 2.0 bus on these devices, we would cut this down to about a half an hour to sort the entire data set with less than 50,000 coprocessors. So mostly we're bus limited at this point, but as these coprocessors improve in performance and the cost comes down, we should be able to do this in a reasonable amount of time. So as I mentioned, the next step is to look at hybrid approaches. Also looking at different device configurations. So for example, those FPGAs I mentioned earlier, if we can configure them to be as physically resistant as the more expensive crypto coprocessors, then we can get much more performant systems. And those are the key points there. Right. So in conclusion, we looked at two different approaches for building privacy-preserving services in the data center. The first one we looked at was a platform for deploying services that would do the personalization on behalf of the user interacting with an untrusted service. And then we implemented an example of that with location-based search. And the second project we looked at was how we can change the ORAM model to try and improve parallelism and get better performance in a real-world scenario. And I'll take any questions now.
Sort of services, untrusted services that you have looked at? It feels like this big map. It's hard to imagine that I have to sort of not trust Microsoft. And in some locations, I understand it's highly sensitive, but a lot of cases, the location itself may not be so sensitive. So
we did look at a few other examples. We used Bing Maps here because it was the most straightforward to implement, and we had interesting information about the data set itself. So other services we looked at were location sharing among your friends, for example. So if you want to use an untrusted service to coordinate with friends your current location, you want to keep that hidden, and without having to involve key management among all the different friends. Another example of a service we looked at was plagiarism detection. So for example, if you have a bunch of conferences that are submitting around the same time, and you want to be able to check that none of the papers are plagiarisms, that they've been simultaneously submitted to multiple conferences, but you don't want to reveal what those submissions are to anyone. We can implement a service like this that could receive the two results and check and respond whether or not a plagiarism was detected. Another example of a service would be working on the aggregate information I mentioned earlier. So if you can have essentially a large database that's only accessible by our trusted module, it can collect aggregate information and provide, say, recommendations for Netflix, for example, without revealing whose search history to revealing the search history to the untrusted service. So working on encrypted search, for example, is another example system.
Could you compare your work with the related work?
Okay, yeah. So the HyperSafe system that we're working on has a lot of similarities to the TrustVisor system. One of the differences, though, is we're able to still communicate with the untrusted service. So we can control the exact pages that are being shared between the untrusted service and the trusted service. And this allows us to actually implement a a shim to communicate with the trusted module. So because we are communicating, though, with the outside world through a continuous manner, you will have to design the trusted module to be able to resist any sort of malicious inputs. So in that regard, it's a more performant way of implementing something like Flickr, where you would have our isolated execution environment running our trusted module. In terms of the, let's see, the other services I was talking about were the, like Reprieve, for example. Reprieve, I'm sorry. So Reprieve, as I mentioned earlier, is doing all the personalization locally on the device. So it's going to be limited by the amount of information you have present on the device and what kind of information you can glean from just the user itself. So if you want to get other information, like correlate with similar users, you're not going to be able to do that locally without retrieving that information and coordinating with other users to share their information and establishing an aggregate. And Search on the Go, for example, also uses aggregate information, but that's going to require subscribing to an aggregate, which necessarily reveals which aggregate you belong to.
So I do want to maybe revive the question that J2 asked. I don't want to remember your answer. So the TPM usage, that in the first project,
Yes.
Is that pretty equivalent to having a proxy? And having that proxy, essentially you can imagine Microsoft is outsourcing the privacy preservation to another party, and that's a proxy service. And it'll only give the...
I think the best way to look at it is that the protected module in the data center is acting essentially as the client would act if it had all the bandwidth to communicate with the untrusted service. In our example, for example, the location-based search. So the client would be able to perform an obfuscated query, get back thousands of results, and then do the...
Exactly like proxy. Proxy is a client to the server.
Right. But this is a trusted proxy that's going to be performing the obfuscation for the client.
Yeah, and but if you trust this box as
Proxying the request is not necessarily enough, so just rerouting the request, because the request itself may reveal something. So if I ask for AIDS clinics near Brian's house, then no matter how you route that, it's still going to reveal something about who's making the query. Whereas with this solution, you would ask for AIDS clinics in Washington State, and then the trusted proxy would filter that out.
Filter what?
Filter down to places near my house.
I see.
So,
Well, you could, that's because all the Bing's result went to, right? And you could also design a proxy just to do the same thing. I guess my question is, can you do all of these without TPM, but just trusting?
I mean, you can do it by yourself in this example. You don't even need a proxy.
So, I mean, the whole point of the TPM is to make sure that you can trust the proxy.
Sure. About what? Trust the proxy.
To do the deobfuscation for you.
Oh, I see. So basically TPM is acting on the user's behalf.
Yes. So we have an entity working in the data center for the user, and you can check that it was correct.
So let's say that like thousands of users are using this service, and there should be thousands of trusted modules within the data center.
That's right. And because these modules are very small, like I said, about 100 kilobytes, it should be possible to instantiate thousands of these over, say, an Azure network of VM hosts.
Do you require, does the TPM module need to have the notion of multi-user? Like, there are many users are requesting, making requests, and this is follow-up to James.
You're saying...
Does your TPM module have the notion of multi-user?
multiple users for the VMs?
The multiple users issued, many different users issued queries.
I see. So this is why we're including the client's public key in the query, so that it can be stateless, essentially. The TPM is not involved in handling the result specifically. So we designed this so that there is no interactive attestation protocol. Essentially, it's a secure boot setup. If you did have to attest it, there would be a serious attestation issue you have to handle.
So what can you do to extend this trusted module to act like also proxy, trusted proxy? Let's say that I want my request and someone else's request go through the same trusted module.
So you would have to trust the module to be able to keep the two requests separate. You could instantiate per user TMKs. I mean,
So as long as I and someone else has this key, same public key and private key, so that the trusted module will not care. So there's no authentication or anything, just
right. So the responses that are being given back in this situation are not secret in the sense that someone else had the secret key. Giving up that information is not necessarily bad. Well, not quite that, but yeah, I see what you're saying in this situation.